All right, I think we are online. Good evening, Europe. Good morning, US. I'm very happy to welcome you for our talk in the module Emerging Fields today. Today we welcome Mr. John Lin. John Lin is an aerospace specialist. He has been working 36 years in the field of aerospace and mechanical design. He joined ILC Dover in 1997, and he is the principal engineer of the Space Systems Division. Today we will hear about deployable structures and successful testing of advanced space habitats. And Mr. Lin is primarily involved in the design and the development of space and engineered inflatable and deployable systems and structures. He will soon tell you more about what is an inflatable and deployable system and what are the particularities in an extraterrestrial environment. John Lin's primary technical function is focused on raising the technological readiness level of inflatable products. And this they do by developing and analyzing requirements, developing integrated product concepts. They perform detailed design and fabrication. And of course, they have to test and evaluate those products in a relevant environment. Mr. Lin works on applications for these technologies, and these include space habitats, decelerators, landing bags, and other space and terrestrial structures. A very warm welcome, Mr. Lin. Thank you for your time, and we are very much looking forward to your talk.
Thank you very much, Sandra, for the kind introduction. And any kind of work that is in the front end are typically punctuated by failure, not always success. But hopefully what I share can inspire you on some of the work that we have been doing and how it affects not only space, but of course, terrestrial area as well. So I will now attempt to share screen, make sure everything is working. Okay. Just check that you are able to see the shared screen for the presentation. Okay, thank you for the thumbs up. And if you have questions, you could, if you any along the way, I would suggest that because the timing, you may want to type it into the chat, your question, and so that we can go back during the question and answer to look at some of the question. Because if you wait for the question at the end, you may forget what you were thinking. So I encourage you to put it in the chat. Okay, so for today, the title is about a new development in this technology, but this technology has been around for a while. And so today I'm going to go back and kind of share with you. First, I will share with you about ILC, kind of a commercial. And then in the ILC, we'll talk about a product area called soft goods. And soft goods really is about fabric or textile that are highly engineered. And I will go into that, how we apply those so-called soft goods in our product. And then I'll talk about a little bit about the tensile structure, particularly related to inflatable structure, because tensile structure have tents or other bridges that for those who are in the architecture, you may already know about these tensile structure. But I'm going to talk about a focus on just about the inflatable area, how we use tensile structure in the inflatables. And then we'll talk about what ILC have been doing for more than 25 years in this particular area of particularly inflatable space habitat and how it's advancing. And then I will share with you the recent advancements in the inflatable habitat. And of course, really want to do is look at the future. What can we do with these class of product, both in the space and in terrestrial application, even application on Earth doesn't have to be, always be space or on Mars. So that's the quick outline of what I'm hoping to share with you today. So an overview of ILC Dover. ILC has 3 primary product area. They are in the pharmaceutical, medical devices, and aerospace. And I am the principal engineer in the aerospace. Right now it's a sub-company. Originally we were a division. Now we are a standalone company under ILC Dover. In the pharmaceutical area, we're not the one that makes the powder or the chemical for the drug or the medication. We're actually still in the processing. Our product are containment systems, both in traditional hardware like stainless steel, and also in what I call soft goods. These are special plastic films that are very low permeation, so that the drugs when the workers are making medication, they are not exposed to these highly potent compounds. Likewise, we make medical devices, things like IV fluid bags or other medication bags that you see in the hospital for feedings through the IV system. And so these are the products that ILC Dover are making. And again, most of them are what we call soft goods, so plastics and fabrics. And the company started in 1937. And so the company first made its, in a way, made its product during the war, during World War II. We made a lot of inflated raft. Okay, so these attack raft, canteens, boats are what we made for the product, or emergency raft for battleships and destroyers. So that was the product, and they were made from rubber. And then in the 1960s, that's when we got into the essentially starting with the high altitude suit for spy planes, but then gradually, from the opportunity to bid on the NASA contract, we won the Apollo contract for making the spacesuit. And then from then on, spacesuit has been one of our essentially primary product in ILC Dover throughout the year. And even today, we are still making spacesuit, not only just for NASA, but also for commercial ventures as well. And in the last 30 years, that's when we ventured into the pharmaceutical area, and we developed many essentially IP, our own films that we developed using different plastic systems for lamination, and then we produce these bags that are highly effective in containing different drug compounds. And so here, that shows, because this particular talk about history, is focusing on space, so we kind of give a little bit of a talk on the other the two portion of the company in the medical devices and in the pharmaceutical processing. And you will see that throughout the year, we develop a lot of intellectual property and also have several patents related to these product areas. ILC Dover is a global company, and we do have many facilities not only in the North America, we have in Europe as well, and also in Asia, Southeast Asia. So these are all the facility that we do have. And main manufacturing are up here in Frederica, Delaware. We are, so a lot of people do not know where Delaware is, but we're between New York City and Washington, DC, somewhere in the middle. And so that's where we are. And then we have in El Paso, Texas. And of course, we have a facility in Poland and Ireland and England as well. So in terms of space division, and now it's actually called ILC Aerospace as a company. Within the ILC space area, we have 4 primary product area. And number 1 is spacesuit. And they're not only for the, starting from the Apollo all the way to the station, the shuttle, to even now for with not only the NASA venture, the government venture, but also a commercial venture. We are building spacesuit for Boeing and Sierra Nevada, and so sort of in the spacesuit area. We build spacecraft landing system. We had the opportunity to land successfully 3 spacecraft on Mars, Pathfinder, Spirit, and Opportunity. And I will share with you about that a little bit later. And then, of course, the habitat area, this is what we'll be talking about today. And then another sector is actually lighter than air. ILC Dover produces, I would say, over 300 different lighter than air, either airship or aerostats. Aerostats are used for border patrol, for radar package. And then airship, we are the one that produces the Goodyear, so-called Goodyear blimp is actually produced by ILC, but we produce for Goodyear for advertising. And we also produce the envelope for Zeppelin. And so we will go to Germany and interface with Zeppelin to install the Zeppelin airship as well. So that's ILC's lighter than air portion. Again, commonality among them, you can see, is all these highly engineered fabric or plastics. So here you see 2 pictures. One is astronaut on station, and this, we are currently still supporting all the program for NASA into 2035. And also we are making commercial suit, and this obviously is an artist rendition of a new lunar-based suit, terrestrial suit that will plan to go back, and hopefully we can go back in the 2030s, if not earlier. Hopefully, it could be earlier. So with Sierra, we are working with Sierra Space, producing commercial suit. What you've seen on the picture are 2 of our suit. One is called Astro. Astro is the suit in the white, and that suit is for extravehicular activity, EVA. It's much lighter weight than the current spacesuit that we have. And so mobility-wise will be much better. And so this particular suit, not only planned for space, you can do it for space, but also for a terrestrial application. And then the other suit is called Soul. Soul is the entry and descent suit. And typically right now you will see this suit used by NASA astronaut. They look like an orange suit, like an orange jumpsuit. Okay, that is made by Collins Aerospace. But ILC has this one, so in the black. And so I would say this particular suit is not only fire protection, but much more comfortable than the current suit. We work with Collins on the current suit, but that suit is over 40 years old in its design. And of course, the Soul suit is a much recent design, and it's with newer material and more comfortable. With Sierra Space, we also are working on the space habitat. And this is working on their product called Life, a large integrated flexible environment. And in this particular project with them, we are actually making 6 1/3 scale. And in fact, just yesterday, brand new news, we're actually going to make 7 1/3 scale habitat, and then 4 full-scale habitats by the end of next year. And the scheduled demonstration, we are hoping for LEO demonstration now maybe in 2027. If we can do it in 2026, we will push for it. But I think the launch vehicle schedule goes out to 2027. And so the likelihood will be in 2027. But at the same time, we're actually already looking at a potential habitat that is 2 times or 3 times the volume, and with window in the system. And so this habitat, imagine the habitat you're seeing in the artist rendition, that is not this size, but 3 times bigger. And what you can do with it in terms from an architectural perspective will be very interesting. And even in a small volume, how do you use it in such an environment and be able to use it so the human mind can perceive this environment and not get claustrophobic feeling will be very important. Okay, and this is just kind of advertising our people a little bit. These are our spacesuit team. They worked on the current NASA extravehicular unit, the EMU. And of course, they are also continue to work on these special suit support all the way now extended not only to 2024, but 2035. This is kind of a quick look at our Astro spacesuit. Current pressure capability is at 8.3 psi. You could go down to 4.3, but that will require, if you're aware about a different pressure that the human being can survive, you could survive at a higher oxygen content at a lower pressure. However, you have to do what we call pre-breathe. It's very similar to a diver go down deep into the ocean. As they come up, they need to do some stop in between to let the nitrogen out, right? So likewise, for astronauts, you could go to a lower pressure, but at 4.3, there's an extended pre-breathe period to let your nitrogen come out. 8.3, you don't have to stay as long. We are developing a spacesuit that can operate at 10.5. And if you can operate at 10.5, no pre-breathing is required. And here is the new Boeing ascent and landing. So you see, this is also similar to our Soul. Soul is in black, but the one that we are building for Boeing as a commercial suit is actually in blue. And so this is one of the suits. And we are hoping that this suit will be used with the new command module that Boeing is building. And the command module is called Starliner. And they're going to have the first manned mission next year. And so this particular suit will be used on their first manned mission. And we also mentioned that there is the other side, the other business area is the airbag. And one of that product is for the command module, the Starliner command module. The Starliner command module, when they re-enter the Earth, they could either land in the ocean, and if they land in the ocean, they have a float, which ILC also built. Also, the uprighting back. If you land in the water, you need additional airbag on top of the landing, just in case it flips, it will upright itself. But ILC also prepared this command module for desert landing. So if it does land on a desert, you have less problem with water potentially getting into these electronics. So the land landing is using these set of airbags, and ILC Dover have been producing these airbags, and they've been performing very well in the landing trials. And again, in 2024, the initial plan is for them to land in the ocean, but just in case these airbags are equipped in the command module, if they need to land on land for some reason, definitely it will safely allow the astronaut to land in a lower fourth environment with the airbag landing system. Okay, I do believe that ends the first portion of the presentation. Okay, let me jump out and let me open the other presentation. Okay, are you able to see the second presentation? Okay, good. So as I mentioned, the first portion of the presentation really talks about ILC and the soft goods that's related to these kind of products. And so now we will kind of get into what the more detail of these products from the perspective of the tensile structure, and how do we take some of these ideas and apply them into inflatable structures. Okay. In terms of tensile structure, one of the person that I admire a lot is actually Fred Otto, and I think many of you may be familiar with his work. And if not, then there will be your homework to go into and look at Fred Otto's book. He published in 1965. He did a lot of tremendous great work in this area. He's a German architect and structural engineer. And very notable in his work is a lot of lightweight structure, and particularly with membrane structures. And in 1972, he's the one that designed the domes, the tensile dome for the Olympic Stadium in Munich. And here is a one minute commercial for his 1 hour special series on spanning the future about Fred Otto. And in here, he mentioned about nature, and I think it would be important how we can learn from the structures that you see in nature. Let me play this for you.
People like Fred Otto have a kind of a longevity in terms of ideas, because these ideas were very avant-garde at the time and very progressive. And so therefore, although as 40 years ago, they still are very refreshing.
He brought together engineers, architects, biologists, and the most different fields that even were not connected at this time with architecture.
Fred Otto has shown us how it could look like if somebody is really doing it as an artist, not just as an engineer or an architect, but as an artist.
Frei Otto's work in tensile structures is staggering. He's really the father in so many ways.
What Freud is doing goes beyond geometry. It is tying in with the infinite or endless forms of nature.
He liberated architecture from kind of square and rectangular kind of forms to really make forms which are in response to natural forces in nature, so with minimum amount of material.
We have now the future. The future is not tomorrow, the future is today.
Frei Otto, spanning the future.
So his, I think it's very encouraging that he said that the future is today, right? It's not, we are looking at work that is today. It's not just the future. And that's kind of inspiring. Also, I don't know if you caught it, to produce a minimum lightweight structure, oftentimes you see this in nature. And one of the things that Frei Otto experimented with is on bubbles. Okay, and I mean, as a kid, I love to play with bubbles. I think bubble is just amazing, and it's formed on a very thin film of soap and water. And so when we are looking at what I was talking about, Mars exploration rover, airbag landing system, and you will see that we are trying to produce a landing bag that is lightweight, because you want to send this to Mars, and every ounce of material you want to put it on the launch vehicle for a journey that takes you to Mars is very expensive. And so the lighter you can get, the stronger the material, the lighter you can get, and the better it is. And so when we are designing the Mars airbag system, we want something that has what we call minimum skin stress. Okay, so if you're familiar with the equation of inflatable articles, a sphere is pressure times radius divided by 2. That's an empirical formula. And so you want to do it so that it's as lightweight as possible. And so as you approach a spherical, it will be, you can get to the minimum design. Okay. And so, but in any design, it's not without a lot of hard work. And when we designed this article, not only you need to design in its deployed state, you need to test it in its function. So we did a lot of drop tests, dropping it in different angles. This table here with all these rocks that mimic the rocks that are that you will find potentially on Mars. We tilt the angles of the table, drop and drop and drop to see what we can do. And also, this airbag needs to deploy it out in a very fast, using a gas generator to deploy it out. So we need to see how to pack it so that when it deploys out, it does not lock itself up, and so that it causes the material to, instead of inflating, if your material jams, it will just blow up, okay? And so we need to be mindful of all those design. And so when we are looking at packaging, we also look at nature, right? One of the natural phenomena we see every day is a flower opening, right? And as the flower opening, how does the flower package in the bulb? And so that when it's opening up, as the liquid's being pumped into the flower, it does not cut and jam. And same thing when we are looking at packaging soft goods in this kind of design, we need to look at nature as an example to learn from. Okay, so you see here, this is an artist's rendition of once the vehicle comes in, how it will potentially drop and bounce. And once it drop and bounce, how the system will open. And as it open, it will always sit upright. And then the system will pull all the soft goods, suck the soft goods. And so this is an artist's rendition of what it should happen. And then this is sitting on the Mars surface. The rover came off the landing vehicle and took a picture from the camera looking back at the system, okay, and proving that it successfully landed on Mars. So this talks about looking at a bubble. The other nature, another form that we are, that I personally used, is what we call the teardrop shape, okay? Because teardrop shape is affected by gravity, just like bubble affected by gravity, and it forms a certain shape. And in this particular design, we utilize it for flood mitigation. This auto uses for having a liquid or even dry grain as a facility. You can contain water for water storage or fuel storage. In ILC, we did have a product. We recently sold this particular product line to another company that we built floodgates out of soft goods. And you can imagine this now taking a shape similar to a teardrop shape for floodgate. And it's packaged together and rolled up like a garage door. And when needed, New York City will deploy this door. And this is in this particular system is actually now installed. Several of them are now installed in the subway tunnel for the New York City subway. Okay, and so it will stop flood up to 15 feet of water, essentially going above the tunnel. And so they will stop the water from getting into the subway tunnel system. So that's an application by looking at, again, looking at nature like a teardrop. Okay, and now we'll take a look at how a minimum, essentially, if you look at these designs, why would we even want to use inflatable structure in space? Okay, and obviously ILC did not come up with this initial idea. Actually, von Braun came up with one of the initial idea of using the soft goods, of course, in the early 1950s, and then Goodyear also were using it. Even the Russian space were using it. And of course, during this time period, you can see the from 1 to 5 here. These are done in the 1950s and in the into 1960s. There was a gap in between because they realized that to advance this, there needs to be a material advancement. And it's not until materials such as Kevlar or Vectran that were developed suddenly in the early 1990s, there is a possibility of, again, looking at these systems. And so in early 1990s, a TransHab was envisioned. And from TransHab, there were many other development, such as a toroidal habitat or the expandable habitat. Of course, Bigelow did a small called Beam, and this particular system is still now on International Space Station. Okay, and so this is a progression, of course, because the material advancement from not just nylon. Nylon was one of the earlier material, but once you get to Kevlar or Vectran, suddenly you have a much better material to work with. So this talks about TransHab. It was done in the early 1990s, 27 feet in diameter. And in fact, the current life module will have the similar size to this. ILC Dover, working with NASA, developed these two potential ideas, and both of them are inflatable. You can see not only the habitat module itself, and also even the airlock can be, and this can be packaged down into a lander system that's even smaller than the original lander on the moon. And the idea is be able to land the system on the moon. This system was designed for 9 PSI operation, and it is designed for what I call minimum mass. Again, right? Talking about bringing down the weight of the air barrier to as small a mass as possible. And this is the toroidal habitat, again, ILC working with NASA JSC, that is also a 9 PSI system in a toroidal form. And the idea of this particular habitat is for, if you see the artist rendition, is for central hub of lunar base, okay, initial central hub of lunar base, and that they can connect through these nodes that then connect to other vehicles. And other vehicle potential that can be used are what we call the XHAB, extendable habitat. Again, ILC Dover working with not only NASA JSC, but also with Langley produced this particular system. Again, operational pressure at 9 PSI. Minimum, again, trying to design the minimum skin for the system. And here is the artist rendition of how you use that particular system. To develop the how to use these kind of system, ILC Dover developed this particular inflatable habitat. This inflatable habitat was developed in conjunction with not only NASA, but National Science Foundation. And we produce a habitat that can withstand 100 miles per hour wind. And it's air beam. I don't know if you're familiar with the air beam, but it's an air beam system. And you take the package, can be packaged into a small pallet. You bring it out. And here the picture you see is in South Pole. This system was deployed in South Pole. And because of the air beam system and the circulating air, it has a tremendous it's tremendously effective in terms of its insulation value. So it was able to not only survive the 100 miles per hour wind, but can be used even during the winter time in the South Pole. ILC Dover, in conjunction with SIXA and Hamilton Sundstrand, and working for a project for NASA, we developed what we call a minimum habitat system. And that in that particular project, we looked at what is required to be sustainable on the moon with the minimum amount of space. And here, obviously, is no longer a minimum structure in terms of skin stress, but it's a minimum in terms of what we need to bring so that 3 astronauts can indefinitely stay with only supply mission coming down. And in all that, we have to look at all these different areas or different subsystems, right? You need to have your life support. You can need to look at your living space and how people in such a small space, psychologically, how do they behave? And what kind of experiment you can do, what kind of storage you will have, and what kind of system you will need to in support of this kind of environment, such a small environment. Okay. All right. So now going into a more recent work, that is done in the last 2 years. And I'll start with this particular video.
This may seem like a moment gone horribly wrong. But catastrophic failure, in this case, is the whole point. Here at Marshall Space Flight Center in Huntsville, Alabama, where NASA has tested rockets and other spacecraft for more than 60 years, the work today is down in the trenches.
We're actually standing in the flame trench on the test stand that tested the first Saturn I rockets for the Apollo program.
Engineers at Sierra Space are using this historic site to take a subscale version of its inflatable space habitat to ultimate failure. They will inflate this unit with gaseous nitrogen until it bursts under pressure. It's just one of many tests along the path to NASA certification for the company's life habitat.
Life is our large, integrated, flexible environment.
Beth Shapey is the lead engineer for this ultimate burst pressure test. The full-scale life habitat will inflate to the size of a 3-story apartment building on orbit, which is exactly where Sierra Space plans to put one later this decade.
So this here, this blue is our test stand. This holds our article in place while we pressurize it. Some of these lines, all these are data cables. So these are measuring the pressure or the temperature. We've multiplied our number of ground anchors by 4, chains going kind of laterally in an X pattern across, and that should keep this thing down once all the pressure releases.
James Kerwin is with ILC Dover, the engineering firm that builds test articles for Sierra Space. The goal is to repeat the results of a successful burst test that happened just a few months ago at NASA's Johnson Space Center.
We'd like to demonstrate repeatability. That'll show that our design, our manufacturing processes, our quality processes are all repeatable from one test article to the next.
On today's test day, we've been working towards this for several months. It's going to be fantastic. A little bit of rain outside.
So it's currently raining right now. So we have actually 3 tarps over the test article to keep it dry. We're gonna go to 2 PSI, should take 30 seconds or less.
When the rain lets up, NASA managers make the call to start the test.
All right, BJ, let's go ahead and add a little bit more pressure.
The goal is to climb past 180 PSI, or pounds per square inch of pressure, NASA's threshold for certification.
Pressurize up to 120 PSI for a 5-minute hold.
Yeah, let's go! The previous Sierra Space test exceeded that mark, bursting at 192 PSI. As the pressure increases, the team anxiously watches the numbers climb even higher than the first test.
199, there it goes.
Until...
Burst.
We just had a successful burst test at around 204 PSIG, which is way higher than last time.
Down in that soggy flame trench, not much remains of the test article. Its woven fabric is scattered, tattered, and torn. But the life habitat has passed another critical test.
A little bit of debris, a little bit of shrapnel.
Yeah, a little bit of carcass left on there.
Yeah, you can see the core still remains.
As the team inspects the scene of destruction, they're already looking ahead to next year. They plan to bring a full-size module, 27 feet in diameter, to ultimate burst pressure right here. You might call it the next Big Bang. I'm John Zarella for Sierra Space.
That's a wrap.
Impressive.
So I don't know if you will notice, but they're saying they're chaining everything down to the floor. The explosion was such a force, actually, it moved. So you can imagine you never want to have this thing explode. because it will take out not only the system, but it takes out even the test stand. Okay, so we mentioned that this is a what we call LIFE, large integrated flexible environment, and you see again that this is the artist rendition. The deployed volume is nearly just 280 cubic meter, but including if you include another node, it actually approaches 300 cubic meter, which is 1/3 of the current space station. And that's how big this thing is. And it's going to operate at 14.7 nominal pressure, and therefore it actually needs to go to 15.2 psi. Remember, we were talking about in the previous, when we were doing development, it was only in about 9 psi. This is now almost double that pressure. And so the material, because we're now using a much better capable material, we can essentially inflate it to 1 atmospheric pressure. And the material can survive at least 15 years and potentially can be extended even longer if the protective layer is there to do the work. Okay, and because it is a soft goods structure and it's never been flown in this kind of environment, and therefore NASA requires certification, just like any building requires certification for occupancy. So NASA have give us essentially a space building code for that. On Earth, you have building code. Now space have a building code that you need to live with as you design. And so these are the code or the requirements that we are using for this particular type of article in space to pass all the requirements before we can bring it up into space. To test it, and that's why we call it what we call it ultimate failure methodology. We need to test it until it bursts. So we understand what it means, how much safety factor we have on this article. To test the full scale is very expensive. And so we are using 1/3 scale and be able to appropriately scale not only the material usage, but at the same time, we don't want to be too small so that it's not representative of the stress in the skin. And so 1/3 seems to work very well. It's large enough so that the full scale material is not does not get a correlation. Essentially, you need to correlate your test article with your analysis. Once the scale was able to correlate very well from your analysis to the test result. And so here is the test article that you saw in the burst test. And we obviously produced multiple test articles. The test that you saw earlier on is test article number 2. And you've seen this picture and the way we set it up. We have to instrument all the test articles and bring it what we call UBP, ultimate burst pressure. So as you bring it up, the pressure, you need to slow it down, allow the article to find its place. You don't want to inflate too fast and not too slow. And so there is essentially a storyboard that we need to go through as we bring this article up to pressure, and then hold before the ultimate pressure is reached. During the same time, we actually have a lot of scanner on this article, so we can go back to look at from the scan to see not only that it bursts at a particular pressure, but what the skin stress it is seeing by measuring. You can see that this white thing has a lot of dots on it. So the camera can pick up those dots and the relational distance, and you can go back and look at the skin stress of these articles. Further tests, right? So not only are doing the ultimate burst, but we're also doing what we call a long duration creep test. As this article sits in space or in an environment, could be on the moon or Mars, the material may still move. and may still creep. In these kind of fabric structure, creep is an enemy, and therefore we need to understand what the material is doing during the life of during its life in the application. And so we have also done the creep testing, and the testing went very well. And so we are now be able to correlate not only the creep test data, but also the ultimate burst pressure test, and be able to see and comfortably see that this article, although designed to 4x, maybe we don't need to anymore. Maybe we can design to, just like aluminum, to the 2 times the safety factor rather than to a 4 times. And if we could do that, we can easily increase the size of these habitat. Okay. So in terms of design factor, I just mentioned, if we can design this instead of to 4x, 4 times the safety factor, then we can reduce it to 3, and suddenly we can reduce the mass, and suddenly we can increase the size if we don't reduce the size, right? And you can increase the size and have the same mass, and the more room you can have, and the better the system may potentially be, right? So that's why we are now discussing with NASA, with the successful tests behind us, that we can potentially reduce the safety factor from 4 maybe to 3. Okay. And so this kind of gave us a quick conclusion of the recent work, and now we are building the full-scale certification unit. And this particular unit was also built by ILC. That's a demonstrator, and this unit is sitting in Sierra's their facility. And we are hoping that as we build the first certificate unit, that we'll be able to bring it to the first full-scale burst test later this year. Okay, so what's the future? What's the future? And hopefully this last video can inspire us looking into the future. Before I start the video, you could see that what we have done now, besides just the soft goods, we integrated this particular hardware. And that is where window or other instruments or exterior equipment can be mounted to. And that's why we designed this hardware, so you have a soft goods to a hardware interface. And we are now testing this, and this is the test showing that even though in this integration, there's no detriment to the article.
I'm at a place on a base that's for NASA, and I'm testing the next generation of habitats, which are going to let us build a platform in space that's going to benefit life on Earth. Now, when you launch in space, you got to have a destination. We build the destination.
The life habitat provides the volume for the astronauts to really reside in and live and sleep and have recreation, do their science, kind of live inside the life habitat.
If you think about what it costs to launch a habitat, you want to get the biggest bang for your buck, right? You want a small when you launch, large when you deploy. That's what soft goods brings to the table. We launch these soft goods packed, soft around a hard shell, which is our core structure. So you might pack it to 40 or 50 cubic meters of volume. When we launch it in space, we inflate it, it goes to 300 cubic meters. So your mass to volume launch is really impactful. So Life Habitat, we launch a single habitat, we get 1/3 the size of the International Space Station. But that's the Life Habitat. We have habitat designs in our product evolution line that we could launch in a single launch and be the exact same size of the International Space Station. The technology is limitless. When you link this to what we have to do for space exploration. So we've been talking a lot about low Earth orbit, so up near the International Space Station. We're developing product lines which service cislunar, and then we also have technology which supports us on the lunar surface, and then technology which brings it to deep space. When you talk about deep space, it's long duration missions, over a year.
This is the first time Sierra Space has ever tried to put a metallic plate in this inflatable habitat.
Why a blanking plate? Because that's where you put a window in. What better window in this entire world than if you're up in space and you look down at Earth.
The whole idea of this plate is to create a rigid point and a soft structure that can be used to mount anything to, like a window or an airlock or docking mechanism, berthing mechanism, grapple hooks, robotic arm, solar arrays, radiators, you name it, you can attach anything to this plate.
The misconception is soft goods is soft. Soft goods has two modes, non-pressurized and pressurized. Non-pressurized, it's a textiles. It's whatever type of material it's being made out of. Under pressure, it's a rigid structure and it's stronger than steel.
The ultimate goal from this burst test is to meet or beat the values that we met on previous burst tests.
This is the historic landmark at the NASA's Marshall Space Flight Center in Huntsville, Alabama, where stages for the Apollo rocket were tested. This allowed us to take human beings to the moon for the first time. It's really fitting that we, Aerospace, are now using these same test stands to create the new orbital age. So today's test is one in a series that allows us to take the journey, put our life habitat in low Earth orbit.
In order to certify habitats that be in space, there's a series of gates that you have to pass. That first gate is ultimate burst pressure, UBP testing. What is an ultimate burst pressure? It's what the team loves to do. We take that subscale, we maximum pressurize it, and we make it explode, destroy it.
We in the soft goods and the structural soft goods are pushing those boundaries of the materials for what NASA has a lot of experience with, and therefore we're doing all these tests to understand where it will ultimately fail and what our capabilities are.
All of this testing, all of this development, what we might deem bringing it to failure, is actually bringing it to success. We're failing to succeed, and that's critical in any program. And we're going to continue to do it because we want to make sure our product lines are robust and they're safe.
You'll note in the cylinder section, so where the blanking plate is kind of that flat section in the middle of the test article, that will have white paint and black dots. The dots are primarily to allow us to test and measure the elongation of the webbings. There are cameras around the test article during the test that will be specifically calibrated to see how they move throughout the test.
It's especially important on the other side where we have the blanking plate and you're integrating with this theoretically infinitely stiff structure into your soft goods. And so you want to know how those loads distribute around the blanking plate and adjacent to the straps coming in.
All of these tests give us data, and that data supports going into the full scale. This is tough, it's hard, it takes dedication. But when you see things like this and we land at this test site and we start to do a burst test, it's all worth it. And then right when we're done with this burst test, we move straight into the next design. Why? Because this inspires us. 200! 200!
Like 235. 250 and dinner on James.
Absolutely amazing performance. The team did a fantastic job. ILC Dover, Aerospace, NASA. We were expecting somewhere in the low 200s. You know, to get it 240, almost 250 is an amazing performance. That's a 20% increase from our previous article. And this is fantastic going into our first full-scale design.
Later this year, we're going to do a full-scale test, and we're going to add 2 plates into that one. And that's as the product line evolves, the life habitat's going to be growing bigger. We're going to be adding bigger plates, and we're going to be adding more of them.
We are a complete ecosystem. You've got transportation, which is going to take you to space. You've got destinations, which is going to allow you to live in space. And then you've got applications, which develops the hardware that maintains the environment so you can survive in space. You know, the next 3-4 years, we're going to put something in space. That's our goal. I'm at a place.
Okay, hopefully that last video gave you some inspiration, and that kind of concludes today's talk. And if you have, so I guess Sandra, back to you. I guess open up for questions.
Thank you so much, John, we have many questions.
I haven't had a chance to look at it yet.
Maybe we start with from the beginning, and I would ask the students to ask the question themselves.
Okay.
I think the first two questions are from me. Let me see. Oh yes, please, let me have the first question. Why do you build 4 full-scale habitats?
Actually, originally, the minimum requirement was 2. Now, NASA's requirement was 2. And so it's also always based on NASA requirement. But by looking at it, and later on we say, okay, let's increase to 3. And suddenly we want to increase to 4 because there are more lessons we want to learn in terms of fabrication. How we fabricate on Earth will be important. And therefore, the additional article are not only for more testing, because we want to put 3 of them for the statistical reason of having enough data, but also we want 1 more just to go through all the trials in the fabrication process. Do we damage material? Are there issues that we're going to learn? How do we make it so that's faster? So in those articles, we will improve not only data collection, but also improve the production process of this habitat. That's why NASA may only require 2, but we want to make 4 and more. Yeah, so for really is the significance in the amount of data that we can receive.
Okay, thank you. And one more question, please. You talked about spacesuit pressure. I think this is an interesting topic. You also explained it very well. Thank you. And I have a question because you said the spacesuit has a range of pressure.
Right. So so the lower range is like 4.3. The lower the pressure, the easier it is for the astronaut to move. If you can imagine, when you inflate something to higher pressure, it becomes very rigid. Just like the director of engineering in Sierra mentioned that when you inflate the soft goods, it become rigid, very hard, like a rigid structure. And likewise, in a spacesuit, if you want to maintain mobility, the higher the pressure, the harder it is to design the mobility joints. Okay, and so therefore, in the early days when Apollo are working, they're using lower pressure, 4.3 up to 8, but no more than that, because higher the pressure, the more taxing it is on the mobility of the astronaut. Now, with improvement in design and joints, we are able now to bring it to at least 10 psi, and so that 10 psi reduces the pre-breathe required. Otherwise, every time before the astronaut goes out for an EVA event, they have to go into the airlock and wait and pre-breathe, and so that extends the overall mission time frame. By our ability to increase the pressure inside the suit, it can reduce that time because the pre-breathe time and post-breathe time, they become useless time that astronaut had to sit and wait.
Thank you very much. Philippe, you can ask your
Yes.
question.
My question was if you, you showed a lot of tests, but like on Earth in a way. Do you also have tests like underwater or in deep sea? Because I heard that the comparison to the space is pretty similar.
Right. So in the past, we were some of the burst tests, right? So if you look at the burst test that we did, it kind of destroyed a lot of stuff. Original idea is to do burst tests underwater. Okay, that would be better. However, we realized early on that some of these material are they're sensitive to water. They call hydrophobic, or they will soak up water. And when they soak up water with 100% moisture, they actually degrade the material. And therefore ended up Vectran or Kevlar doesn't want to get wet, okay? So by the way, if you have a bulletproof vest, like a Kevlar vest, don't get it wet. It doesn't like to be wet. And so that will protect the material. So the reason we are not using it, not testing it underwater, is because some of this material just doesn't behave well in a very humid or wet environment.
Thanks a lot.
No problem.
A Kevlar vest doesn't work in the water?
They work in the water. It's just that they would degrade. Material would degrade underwater for long period of time. Yeah. So that's why part of the testing that we do with Kevlar or Vectran, we actually put them outdoor and in the rain, in the sun, in the UV. Kevlar and Vectran doesn't like wet and does not like UV. Okay, so those two are the enemy of Kevlar and Vectran. So again, if you have bulletproof vest, don't put it under the sun. It will degrade your material.
Thank you. Fabian?
Hi.
Hi.
Thanks a lot for your presentation. I was just wondering whether all the EVA suits are produced in one size, or are they tailored to specific people that will be wearing them?
Right. So Apollo program, for example, the whole suit is tailored to the astronaut. After the Apollo program, when we go into the shuttle program, or right now currently the ISS program, these now are sized with they were said it needs to be sized for 95 percentile of the people, from the smallest female astronaut to the largest male astronaut. And so the way we do it is we make them into components, and then so they are now for example, your HUD upper torso area have a particular sizing, and that you can tailor. And then the arm, the leg, and the extremities, they are all tailored. I mean, they're not tailored, they are sized into different sizes, and then they can assemble to tailor the astronaut. Okay, so you have different component sizes, but at the end of the day, they choose the component sizes still tailored for the astronaut to use. The only tailored portion is their gloves. The gloves are so important to fit, and therefore every astronaut comes to ILC and have their hands scanned, okay? Scanned, and then a mold is made of their hand so that we can tailor their glove so that they can feel how they work. It will not lose their textility of how they work in space. It was very important for them to be able to feel what they're working on.
Ah, yeah. Okay. And do you, I mean, efficiency-wise, would it make sense to only send very small people to the moon then? Because everything can be smaller. Or was that never a thought?
No, that was never, that was never thought about doing it that way, right? Because in the beginning of any kind of space program, most these are fighter pilots, right? And they usually are male and with a very larger stature because they were fighter pilots. And so there was never thought of leaning toward a smaller size. But right now, I would say I would say you are being selected not based on your physical stature, but really based on your ability to do the work in space. That's why if you look at the US Astronaut Corps, it spans the spectrum of different sizes, different human physiology. We have astronauts that have very, very big hand, very stumpy big hand, but it's not based on your physical appearance, but actually based on your ability to be able to perform your task in space.
All right.
Yeah, Jimin fact. So Yuri Gagarin, first man in space, he was tiny. He was like 157, and one of the reasons was why it was chosen is because of his size and the reduced weight.
Right. So, I mean, in the very early program, right, you have a chimpanzee that went up, a much smaller capsule and so forth. Yeah, but the US program has rarely been selected based on a smaller stature for that reason. But as other country may have, yeah.
May I have an add-on question to what Fabian is saying?
Yes.
When we imagine having a lunar base, that means every 6 months a new astronaut will come, and probably you will have a suit lock.
Suit lock, yep.
But what's happening with the AVA suits if they don't fit?
Right.
Does it mean you have to change the suit every time a new astronaut comes? And what would you do with the old ones then?
Right. So for lunar operation, the suit, there will be different parts that go down with the suit. And of course, now you're being limited by the size of suit you have to go out, right? So those are the logistics that will happen for that kind of operation. But the idea is that they will bring different parts with them. They will not bring the whole suit, but different parts and sizes will be available to bring, so that in an emergency, everyone would be able to don a suit. And that's in the logistic planning of the mission.
Thank you. We have one question. We have two questions, but the first question from the YouTube chat is question from Electric Overland. For lunar operations where breathable air is in short supply, could volumes such as garages be pressurized with other gases to allow the use of the less constrictive suit?
Right. And so if you know about, at this moment, there is no plan to inflate so-called garages with other gas. But certainly, if you have an air beam structure, those air beam structure does not have to be inflated with oxygen. You may inflate with other gas. However, other gas that you bring, whatever gas that you bring will be expensive, right? If you have to bring it. The idea will be that if you, for example, on a lunar or Martian, if you can use the material that's available there and be able to sinter it out, that will be much better, right? For example, if the moon has ice, that you can use the lunar ice to evolve into oxygen and hydrogen and be able to inflate it with oxygen, well, that would be nice, okay? But the idea, if we're going to inflate an air beam, it will be better not to inflate any of those structure with flammable gas. Both hydrogen and oxygen are flammable, and they will not be the preferred gas to use. You may want to use helium or nitrogen. However, those gases are also rare to find in a remote planet. On Mars, the plan is to inflate it with carbon dioxide because that's what's available on Mars. And so those are for if you're inflating air beams. Of course, inside the breathable environment, you have to have the right mixture, just like the preferred is to have the same mixture as the atmosphere we breathe on Earth, which is, I believe, is only about 30% oxygen content. Does that answer the question for her?
I hope so.
Hopefully.
Because the Zoom link is only for our students.
Oh, okay.
And the questions via YouTube are just in the text.
Okay.
Then we have a question again from one of our students, BK. I don't know who BK is. Would you like? Hi.
It's me. First, I would like to thank you for the very interesting input, especially the part about the ultimate failure methodology was very inspiring to me. And my question is regarding the rover, which inflates and unfolds. And I was wondering if the process is reversible.
Okay, so for the rover design for landing airbag system, the process is not reversible. You cannot reinflate. There's no, first of all, there's no gas carry to do so. But if you have to do a reversal, the design will be very different, right? For example, if you only have to open something, then you open and everything just leave there. But if you have to close it back, then you have to have additional mechanism to be able to do so. So for the rover on Mars, all three airbags are not reversible. They just designed for one-time use, and they're left there. Okay. Of course, if you are a movie fan for the movie Martian, you know that he went to pick up something on Mars to put it on his rocket to get back on the orbit, and what he picked up was the airbag. Okay, so that was just a science fiction, of course. I don't think you can do that, but that's what he did in the movie, in the Martian, for the movie called Martian. Okay, hopefully that answers your question.
Thank you.
Thank you. Then the next question is from Daniel. Daniel Rögner.
Morning, hi.
Hi.
We are currently experiencing a new race into space, and so my thought was, is technology theft an issue by ILC Dover?
Mm-hmm. Say that again, repeat your question again.
Is technology theft an issue by ILC Dover?
Is technology, let me try to understand, is technology an issue for ILC Dover?
Technology theft.
Oh, technology theft, okay. I would say yes, and I mean, yes, in this, I think, you mean technology deficiency in terms of moving ahead for ILC Dover? Is that what you mean?
Yeah, if another company steals some technology.
Oh, still theft
from you.
in terms of technology
So
theft. Okay,
Yeah.
yes, that's always the case, and therefore, yes, we therefore we don't always, like, for example, today's presentation is public, right? Most of these are published, and they are on YouTube. They are so there's nothing in here that that people can glean. I mean, people still can glean information, but all the information I share today are in public domain. But things that we, obviously, there are material secrets that we will not even put it into a patent, for example. It will strictly be trade secret. Things like the chemicals makeup of a particular material, or how we make it, those are trade secret. Yes, people will try to, so we need to keep a good security of our data, because people do, and we do experience people trying to steal our material secrets. Yes, that is the case.
Thank you.
Mm-hmm.
Bernhard?
Yes, thanks for the talk.
Mm-hmm.
And I have two similar questions. First of all, do you produce your own materials by yourself? And my second question is also related a little bit to the material. Because I think the protection from cosmic radiation is in the long term one of the limiting factors.
Mm-hmm.
Do you make any research how to protect the people from cosmic radiation via systems or material? Because thin and light materials is, I think, a very bad protection.
Mm-hmm. Right. So, first of all, in terms of material, ILC Dover does have a material group that we come up with brand new material. So brand new material in the sense is that not like you can produce a new basic element, right? You cannot do that. But how do you combine them to come up with new polymers? Yes, we do. Part of the work that we do here is to produce those polymers. Sometimes is using some of the polymer already produced by other chemical company, and then just tweak them and then combine them to make new application. And so, and some of these materials that we use for medical, pharmaceutical, and even in the spacesuit area, yes, they are IOC produced material that we will do laboratory run. And then when they are proven, we may send it outside to a larger company that will make production runs for us. But of course, we have non-disclosure agreement with those companies to protect our intellectual property. In terms of cosmic radiation or high energy radiation, we are looking into how to protect our astronauts in those circumstances. One of the worst material is actually not soft goods, but aluminum. So far, all our spacecraft are made out of aluminum. When aluminum are being bombarded by these high energy radiation, they produce secondary particles that are very harmful for human beings. And therefore, our astronauts can only have a limited lifetime in terms of being in space, because they get a radiation doses like you get radiation treatment for your cancer. There's only a certain amount of dosage that you can take without getting killed immediately. And so, yes, there's a problem with high energy radiation. The best material is water. Okay, the best material to protect our body is actually water. And so you need very high hydrogen content in the material that you produce to block these high energy. And therefore, we are researching into how to produce those material. But you know, hydrogen, again, flammable, and therefore there is a balance. How do you make the best material that are similar to water, but not higher than that, right? So maybe soot that is embedded with water or ice or some kind of gel that have high hydrogen content, like the water content, may be the solution for these cosmic radiation. And people are working on it. I mean, I've been working on that subject for 20 years, but to bring a water gel as a suit to space is very expensive because they're very heavy. So, did that answer your question?
Yes, thanks.
No? Okay. Mm-hmm.
We have a similar question, maybe by Concepcion.
Yes, I have the question about the materials too, but I understand now.
You understand now? Okay. The same. Okay.
Yes, with the question.
And Marlene?
I think the one question was answered already, but a different question I had is how the materials like decay over time. Is there any research on how the material reacts to space long term?
Yes. So all the material that we are using, many of them have gone through. I'm not sure if you are familiar with this experiment called MISSY. MISSY experiment take these materials and they bring them to International Space Station and have them exposed to the space environment. And so a lot of these data that we are currently have are from the MISSY experiment that was done, a decade back in space. When we continue to look at these material, we will expose them to different environment, but it's very difficult to produce radiation environment on Earth that is like in space. And so we continue to put up different MISSY experiments with NASA to take these material up to space, open them up, and have them face the outer space and have them bombard with different radiation, cosmic or solar or UV, atomic oxygen, of course, as we mentioned, these high energy particles. And so, yes, we do collect them and we examine them, how to protect them, and so that we can use them in these habitat. And so when we say that we can have them for 15 years, of course, they need to be protected from all these environments and still survive for 15 years.
So how long are the structures supposed to be in space? Is it only like a year period or is it long term?
So this is a long term. For example, the product that we're building, this Habitat for Life, these modules is designed for 15 years. So they need to survive in space or wherever the environment they're going for 15 years.
But has there been like a research to test out the material for 15 years then, or is it just a learning by doing process?
Right, so these are material, you can go through what they call accelerated aging. And so we test them by bombard them with higher doses of radiation in a faster rate. And be able to find out what happened to them. For example, some plastic will become brittle. If you've seen some of your plastic parts that you've seen, if you put them in the sun, in the UV, they become brittle and they will just shatter. So we do the same thing for these materials. We put them in chambers to accelerate the radiation bombardment. But as I also mentioned, some of this radiation cannot be reproduced on Earth. Like high energy particle is impossible to do. And therefore those you have to put up in space. And some of the material that we are using now have been in space for that to be exposed for that period of time, already up there for 10, 15 years.
Okay, thank you.
Welcome.
Thank you. Milomir?
Hello, John.
Hey.
So I've been working on my thesis the last couple of months at and with ESA. One of the projects was to have an inflatable lunar habitat. So I have a few questions, but I'll start modest with you. So so there might be like a problem with having materials that basically expand and in, let's say, sorry, I'm a bit sick as well. So in very low temperatures, the materials may not behave as they should, and they may not react as we wanted to, like creating stresses, like thermal stresses with, for example, the bladder. In what way do you think that we might need to heat or preheat them during the inflation or right before that?
Right. And so you're right. So these material behave differently in different temperature regime. Okay. And so so if you need to an example, I think you're working on, if you're working on it, then you know that if you launch into space and deploy right away, the temperature will be closer to whatever the temperature inside the fairing. Okay. And so if that's the case, then it tends not to be very cold. However, if you are not going to deploy this package right away, and you're going to let it sit in space, let's say in the lower Earth orbit for extended period of time, in that environment, then gradually you're going to lose a lot of heat. And when you lose heat, then the system is going to be cold. And these material, as you know, if they are resin-based, when they're cold, they can become brittle. And then when you inflate, they can crack, right? And so if you are in that kind of environment, yes, then you need to heat. You need to have heat to be able to heat the package to apply what they call pliable temperature, or to a room temperature, maybe 24 or 20 Celsius, then inflate. Okay, so that's a typical things that dealing with these kind of resin-based fiber or fabric, and you need to bring the temperature back up if you become cold soaked in the environment that you are intended to go to. Does that answer your question?
Yeah, and how would you do that? Would you like
right? So to do so, you would have to either have inside you have a heating source, because most of these are packaged. You heard in the video presentation, they package onto a cord, right? A rigid core. So inside your cord, you would have to have a way to heat up the air in there so that you can heat up the system. And so when you send it up, you would have to have additional vehicle that would have to have radiator or solar panel, allow you to collect the power, so you'd be able to heat up your system inside before you deploy.
Great, thank you.
You're welcome.
Another question before we go with the other ones is about the restraint layer. So you've shown projects with different weaves, like open webbing mesh and a closed basket weave, like using TransHab. So after experiencing all of those, what would your current choice be and why?
Okay, so in terms of restraining the whole system, you on the outside of all these webbing you see, you actually have more, right? You have your what they call a micromedia layer. So those layer, on top of those layers, you would have to have a restraint system to package down. And so it's a combination, right? Depending on how you package it. It could be a webbing system to cinch it down, or a fabric system to wrap the whole thing down. Okay, and then you will obviously cut those webbing or fabric with some kind of a pyro cutter, and then allow the whole thing to open up. So it would depending on how your design is going to package it. So it could be different type of other fabric or webbings to package it.
Thank you.
Okay, you're welcome.
You, Bernhard?
Yes, one short question about are there any safety mechanisms if there is a damage in the shell? Because living in such a building, I think, is psychologically very hard when you know only air keeps you alive. Yes.
Right, and so that is it's true. There's psychological effect, right? So even in the aluminum shell, there have been penetration by micrometeors or debris, and so they have a way to shield up a portion or be able to fix it. Okay, so likewise for these so-called soft goods habitat, there are ways to patch it very quickly. So they will have patching kit. So this is true also for the aluminum system. When they penetrate, they have a special patching kit. They can patch to be able to find where the penetration is, and then quickly apply the patching kit to the system. So again, it's no different from the aluminum system. Both the soft goods and aluminum system require the repair kits to be on station for quickly to make those fixes. So hopefully that answers that question.
Yes, thanks.
Marlene?
I think the question I answered already. I asked already.
Okay, thank you. Alexander?
Hey, so when you were talking about the life habitat, you were also mentioning that it was reduced in safety level from level 4 to level 3. And I was wondering in what kind of difference this is making in terms of the parameters. Like, for example, are there then more people allowed if the safety measures are lowered, or what is the difference for the people using the life habitat in the future?
Okay, right. So in terms of safety, is actually a structural safety, right? For example, when you're building a bridge or building a building, when you're designing your structure, there is a safety factor on the structure, right? And typically when we are designing pressure vessels, for example, when you are building a water tank or building a propane tank for building application, these tanks are made out of metal, and their safety factor are usually 3 or lower, okay? And the reason you can go to a lower safety factor because all these tanks goes through, in their development, goes through ultimate burst test to develop this product. Now, NASA initially dictated that we need to design this structure to 4 times the safety factor. And therefore, it requires certain amount of material, structural material, to be in the shell, okay? And so now, if I can reduce it to from 4 to 3, I can make the shell lighter. And therefore, it reduces from one perspective, if I'm not increasing the size of the habitat, I can reduce the launch load. And that's money, it's saving money. In terms of every ounce you launch, there's a certain amount of money associated with that mass going up. And so if I can reduce from 4 to 3, I'm saving money in terms of launch load. Okay. And of course, if the flip side, the other side is that then I can make the system larger, right? So that with the same skin stress now, I can, with only a 3x factor instead of 4, I can make the system slightly larger and still good. And therefore, I give the customer a bigger volume for their room. And so that's how you play this game. But most immediate reduction in safety factor is reduction in cost of the launch.
Thank you.
You're welcome.
Thank you. Milomir, you have another question?
Yeah, so you've shown some testing with aerospace, with the restraint layer, how much pressure you can take. Do you do the same kind of testing for the packing and inflation process? Like, how would you confirm that?
Yeah, so yes, we would do that. When we were developing the Mars rover landing system, and we had to do it packaged, and then we had to inflate it. Okay, same thing here for the live habitat. We will have to do the same thing. When we get to the full scale, we will package it, and we will inflate it and do an inflation test. Now, the difficult part of this kind of inflation is always gravity, right? Because in space, you don't have gravity, but on Earth, you have 1g gravity. How do you mitigate the gravity? It's a tricky part. So there's a plan to deploy this in a vacuum chamber, just like TransHab. We will package the whole thing, put it in a vacuum chamber, try to put enough mitigation for the mass, and do a deployment test. So that needs to happen. And then after that, you will do your launch, then you will see if the behavior is the same when you deploy it in space. So that's neat. That definitely work are required to do those things.
How would this mitigation of mass work?
So you need to somehow offload. Everything on Earth have you have to multiply by 1 gravity, right? And so you may have to hang different weights using different offload lines so that you can try to simulate zero gravity. Not easy to do. Not easy to do.
Thank you.
Thank you. So we have 2 questions left.
Okay.
Maria, please.
So I was wondering if some things can still malfunction in space, or if the results differ in space from the ones on Earth, because the circumstances, surroundings, and environment is completely different here on Earth and can't be transferred one-to-one to space.
Right. And so you're right. A lot of these tests cannot transfer one-to-one, and therefore you have to make what we call educated extrapolation. Okay. For example, it is very difficult to say to put a material in the space environment for 15 years before you implement, and therefore how to do accelerated aging is important. How to but at the same time, of course, like Missy experiment, we put material up there just to prove out those kind of system. But in terms of analysis, so we take the basic environment and we look at the analysis. And from the analysis, we conduct the testing. And then from the analysis and testing, we look at how they correlate and then how you extrapolate. Because, for example, I mentioned creep testing. Creep testing is an event that goes throughout the life of the product, but we cannot do that creep test in real time. And therefore, you have to accelerate it and then use mathematics to do the extension of your graph and say, here's what I predict could happen in the future. And then you have to trust. But then so every step of the way, you do what we call empirical testing with analytical result, and then you try to correlate the data, and you learn from those data to do the extrapolation. But that is true for many of the scientific area. Even in the building, right? It's very hard to predict what a building could do, a real life-size building would do in an earthquake that is 8 or 9 Richter scale, right? You can't predict it. And therefore you have to build models, you have to do your testing on a smaller scale, and then try to find the answer and then extrapolate your answer. And so here is very similar from the architectural or civil, from civil engineering to space. We cannot predict all the environments, and therefore we learn as much as we can, and then using mathematical equations to extrapolate. Okay, is that understandable? Answer your question?
Yes, thank you.
Mm-hmm.
Thank you. We have one more message from YouTube. It's from Corradi Testi. He says, or he writes, thanks for the presentation. How much do you think you're going to get in mass for a module at launch?
Oh, that would depend on the size of the system. Right, this moment, actually, we do not know. For example, a live module, at this moment, we do not know what the mass will be, but we will hopefully reduce the mass. And right now, even the work, we're trying to reduce the mass as much as possible because it will depending on the launch vehicle that we're trying to get on. I know the launch vehicle gets more capable every day, but it's a lot of money to launch anything. And so, so at the moment, for the live module, we do not know what the mass is yet. So I wouldn't be able to answer that question at the moment. But gradually, I would say before the launch, we will find out what launch vehicle we get on, then we will know what the mass is at that moment.
So we give Milomir the last question, please.
Hi, so since we have some time, I'll pick your brain some more, if it's allowed.
Okay.
I have 2 questions. Maybe I'll start with the lighter one. So since you work on the spacesuit with Sierra Space, and there's this recent announcement that you're going to collaborate with Prada, as a non-engineer working in like a lot of with engineers, it's always interesting to me to hear from your side what you expect from this kind of collaboration.
Oh, okay. I mean, in terms of collaboration, I think engineer to engineer collaboration is always very good. Sometimes you do need to protect your company, and so you do have lawyers on both sides, right? And so lawyers and company managers will set up the boundary for you to share or not to share. But typically in engineering collaboration, for example, working with Sierra, that collaboration has been very good. At least for me, because a lot of people, I mean, the community is small. The people that you have met, you also met in other companies already. So I would say a lot of people that you work with, for example, the people that I work with in Sierra, they were my colleagues or coworkers, even from ILC, prior to they going to Sierra. And so those relationship continue to exist. And so that's on the personal side of working with Sierra. There's a lot of friends working there as well. So hopefully that answers your question in terms of how the feeling of cooperation among engineers. Yeah.
I think also that Prada is not, Axiom is working with Prada, right? Not ILC Dover.
ILC Dover is, say that again, ILC Dover is
not working with Prada, the fashion designer.
Other designers, other spacesuit?
Maybe the question would be, have you considered working with an industrial designer or fashion designer?
Oh, yeah, okay. Yes. In fact, I mean, that question is good because we have industrial designers and fashion designers among our team. Yes. So our suit have gone through fashion design and industrial design to look at how appealing they are, because one of the things we've been told is that your suit don't look cool enough, not like a suit in Hollywood. So we do need to right now. Yeah, we do have fashion design people in our ranks that design and looking at suit design as well as besides the engineers.
Milomir, that's it?
Yeah, if we have time for one last question, maybe. It's about like the layering of the soft goods. Since the patent was for Transhab, it got to Bigelow to build the beam module. So I'm wondering what has changed since then. I mean, the layering, like the MMOD and the MLI, they have the same purpose. How much did it change for you guys in the last couple of 20 years, 30 years? So?
Right. So the change will be in the material improvements. Okay. In terms of MMOD, you will always have MMOD, but in terms of how effective those materials disperse, disperse the particles, they change, right? And you get some very advanced material now that does a better job, and therefore potentially it will be lighter weight, could be thinner material, and the more you understand how those materials behave once they collide with the first layer, how they disperse, it changes the sequence of the layup. And also with newer material, you're able to learn not only those material have a property to stop the micrometeor, but they also have thermal properties. And so they start to work together and reduce the mass overall. Now, in terms of the structural layer and the bladder layer, again, the same thing. Material improvement have made significant stride in the recent decade, and so some of the material that were proposed for Transhab is either no longer there, or we have newer material that is much better than the Transhab material.
Cool, thank you.
Thank you very much. I have the pleasure, or I take the pleasure to ask the very last question to you. And maybe it's a bit difficult or not too serious. My question would be, what are the 3 most important challenges to solve before we can have an international lunar base on the moon? What do you think?
The greatest challenge is for human being, I would say, for personally, is focus. Right, most of the time is as these important things, these events are being led by different nations. Tendency is to lose focus. For the U.S., from personal experience, I started working this 24 years ago, right? On the space habitat project to go to the moon 24 years ago. Every 8 years, we go through a cycle. Why every 8 years? Because the president changed, the politics change. And fortunately, NASA is tied to the government in the US government, and therefore you lose focus. And so I've gone through 3 cycles of potentially launching this, and we haven't have a lunar base, right? And so number 1 question is, can human beings in the current environment remain focused on developing this for the future? And so far, I mean, I like to be optimistic. I'm hoping that this will happen, but unfortunately, it tends to have this cycle of not happening. So hopefully this time, because there are some commercial ventures, people are interested, like SpaceX or Blue Origin, and these now become commercial company who are interested in other reason than military, then hopefully it could happen.
Let's see what happens next year and in the few years to come.
Oh yes, definitely.
Thank you very much, John. It was a wonderful, great, informative lecture, talk. Thank you so much for taking the time.
You're welcome.
For our students, and I hope you have a great day.
You too. For you guys, have a good night.